The discussion will cover conduit calculations, wire ampacity calculations, voltage drop calculations, and SCADA circuit calculations. Firstly, examining the existing conduit. It is a 1-inch PVC underground conduit with a length of 700 feet. The additional conduit is also a 1-inch PVC underground conduit with a length of 700 feet. Now let's proceed to the wire ampacity calculations. For the existing circuits, there are 3 number 10 copper wires for a 30 amps blower motor rated at 30 amps. There are also 3 number 10 copper wires for 120 volts receptacles. The calculation is 20 amps multiplied by 3, which equals 60 amps. There are also 3 number 10 copper wires for grounding, rated at 30 amps for the blower motor. For the additional circuit, there are 3 number 10 copper wires for a 20 amps pump controller, rated at 20 amps. Now let's look at the voltage drop calculations. For the existing circuits, the blower motor has a voltage drop of 30 amps multiplied by 700 feet multiplied by 0.12 ohms per foot, which equals 2.52 volts drop. This is acceptable with a maximum 5% voltage drop. For the receptacles, the voltage drop is 60 amps multiplied by 700 feet multiplied by 0.12 ohms per foot, which equals 5.4 volts drop. This is also acceptable with a maximum 5% voltage drop. For the additional circuit, the pump controller has a voltage drop of 20 amps multiplied by 700 feet multiplied by 0.12 ohms per foot, which equals 1.68 volts drop. This is acceptable with a maximum 5% voltage drop. Now let's move on to the SCADA circuit calculations. There are 8 number 14 copper wires for 24 volts DC SCADA. Information about the voltage and current are not provided. In conclusion, all circuits meet the voltage drop requirements for their respective applications. The existing conduit is large enough to accommodate the additional wires. The calculations indicate that the proposed wiring is acceptable for the intended use. The voltage drop calculation is a crucial aspect of electrical design to ensure the proper functioning of equipment and prevent overheating or damage to the wiring. The formula for voltage drop is voltage drop equals current multiplied by distance multiplied by resistance per unit length. In this case, the resistance per unit length is given as 0.12 ohms per foot for the number 10 copper wire. The acceptable voltage drop is typically 5% of the supply voltage. For a 480 volt system, a 5% voltage drop would be 24 volts. For a 120 volt system, a 5% voltage drop would be 6 volts. For a 240 volt system, a 5% voltage drop would be 12 volts. The calculations show that the voltage drop for each circuit is well within the acceptable limit. The conduit fill calculation is also important to ensure that the conduit is not overcrowded with wires, which can lead to overheating and damage to the insulation. The NEC specifies the maximum allowable percentage of conduit fill based on the type of conduit and the number of conductors. In this case, the conduit is 1-inch PVC underground, and the NEC allows a maximum of 40% fill for 3 or more conductors. To perform a conduit fill calculation, you need to know the cross-sectional area of each conductor and the inner diameter of the conduit. The cross-sectional area of a number 10 copper wire is approximately 0.211 square inches. The inner diameter of 1-inch PVC conduit is approximately 1.49 inches, which gives a cross-sectional area of 0.864 square inches. The total cross-sectional area of the existing conductors is 3 multiplied by 0.211 square inches for the blower motor, plus 3 multiplied by 0.211 square inches for the receptacles, plus 3 multiplied by 0.211 square inches for the grounding, which equals 0.1899 square inches. The cross-sectional area of the additional conductors is 3 multiplied by 0.211 square inches for the pump controller, which equals 0.633 square inches. The total cross-sectional area of all conductors is 0.1899 square inches plus 0.633 square inches, which equals 0.2532 square inches. The percentage of conduit fill is 0.2532 square inches divided by 0.864 square inches, which equals 0.293 or 29.3%. This is well within the 40% limit. The Scottish circuit calculation is incomplete because the voltage and current are not given. However, it is important to consider the voltage drop and ampacity of the Scottish wiring to ensure that it is adequate for the intended application. Number 14 copper wire has an ampacity of 15 amps, but it may be necessary to use a larger wire size to minimize voltage drop, especially over a long distance. It is also important to ensure that the Scottish wiring is properly insulated and protected from damage. The NEC provides guidelines for the installation of low-voltage wiring, including requirements for conduit, cable trays, and other wiring methods. To further elaborate, the ampacity of a conductor is the maximum amount of current it can carry continuously without exceeding its temperature rating. The ampacity of a conductor depends on several factors, including the wire size, insulation type, and ambient temperature. The NEC provides ampacity tables for different types of conductors in various conditions. It is important to select a conductor with an ampacity that is sufficient for the load it will be carrying. Overloading a conductor can cause it to overheat, which can damage the insulation and potentially lead to a fire. The voltage drop in a circuit is the decrease in voltage from the source to the load. Voltage drop is caused by the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 5% for branch circuits and 3% for feeders. To calculate voltage drop, you need to know the current, distance, and resistance of the conductors. The resistance of a conductor depends on its material, size, and temperature. Copper has a lower resistance than aluminum, so it is often preferred for electrical wiring. Larger conductors have lower resistance than smaller conductors. The temperature of a conductor also affects its resistance. The higher the temperature, the higher the resistance. Conduit fill refers to the amount of space inside a conduit that is occupied by conductors. The NEC limits the amount of conduit fill to prevent overheating and damage to the conductors. The maximum allowable conduit fill depends on the type of conduit and the number of conductors. For example, PVC conduit has a lower fill capacity than metal conduit. The NEC provides tables that specify the maximum allowable conduit fill for different types of conduit and conductors. To calculate the conduit fill, you need to know the cross-sectional area of each conductor and the inner diameter of the conduit. The cross-sectional area of a conductor depends on its size. The inner diameter of a conduit depends on its type and size. SCADA stands for Supervisory Control and Data Acquisition. SCADA systems are used to monitor and control industrial processes. SCADA systems typically consist of sensors, controllers, and a central monitoring station. The sensors collect data about the process such as temperature, pressure, and flow rate. The controllers use this data to control the process such as opening and closing valves. The central monitoring station displays the data and allows operators to control the process. SCADA systems are used in a wide variety of industries, including water treatment, oil and gas, and power generation. The wiring for SCADA systems is typically low voltage DC. It is important to use the correct wire size and insulation type for SCADA wiring to ensure reliable operation. The NEC provides guidelines for the installation of low voltage wiring. In addition to the calculations mentioned earlier, it is also important to consider the ambient temperature when selecting conductors. The ampacity of a conductor decreases as the ambient temperature increases. The NEC provides correction factors for ampacity based on ambient temperature. It is also important to consider the derating factors for conductors in conduit. When multiple conductors are installed in the same conduit, the ampacity of each conductor must be derated to account for the heat generated by the other conductors. The NEC provides derating factors for different numbers of conductors in conduit. When installing electrical wiring, it is important to follow all applicable codes and standards. The NEC is the most widely used electrical code in the United States. It is updated every 3 years to reflect changes in technology and safety practices. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is important to consult the NEC to ensure that electrical installations are safe and compliant. Grounding is an important safety measure that helps to protect people from electrical shock. Grounding provides a low-resistance path for fault current to flow back to the source, which causes the overcurrent protection device to trip and to energize the circuit. The NEC requires that all electrical equipment be properly grounded. Grounding can be achieved by connecting the equipment to a grounding electrode, such as a ground rod or a metal water pipe. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds the ampacity of the conductors. Short circuits occur when there is a low resistance path between two conductors. Overcurrent protection devices trip when the current exceeds their rating, which interrupts the flow of electricity and prevents damage to the equipment and wiring. The NEC specifies the type and size of overcurrent protection devices that are required for different types of circuits. In summary, performing accurate wire calculations is crucial for ensuring the safety and reliability of electrical systems. These calculations involve determining the appropriate wire size, voltage drop, and conduit fill based on the specific application and the requirements of the NEC. In addition, it is important to consider other factors such as ambient temperature, derating factors, grounding, and overcurrent protection. By following these guidelines, you can ensure that electrical installations are safe, compliant, and efficient. The calculations for voltage drop are based on a simplified formula that assumes a uniform load distribution along the length of the conductor. In reality, the load may not be uniformly distributed, which can affect the accuracy of the voltage drop calculation. For more complex circuits, it may be necessary to use more sophisticated methods to calculate voltage drop, such as computer simulations. The conduit fill calculations are based on the assumption that the conductors are all the same size. If the conductors are different sizes, the conduit fill calculation will be more complex. The NEC provides guidelines for calculating conduit fill when the conductors are different sizes. The information provided does not specify the type of insulation used on the conductors. The type of insulation affects the ampacity of the conductor. The NEC provides ampacity tables for different types of insulation. It is important to select the correct insulation type for the application. The information provided does not specify the ambient temperature. The ambient temperature affects the ampacity of the conductor. The NEC provides correction factors for ampacity based on ambient temperature. It is important to consider the ambient temperature when selecting conductors. This detailed analysis underscores the importance of accurate calculations and adherence to electrical codes for safe and efficient electrical installations.